Welcome to this explainer. Today, we're diving straight into this incredibly fascinating intersection between high-speed racing and just brilliant electrical engineering. I mean, have you ever actually wondered how electric racing motorcycles manage to maintain their blistering top speeds right up to the finish line, even when their batteries are draining? Well, today, we're going to uncover the hidden piece of hardware that makes that possible. We're exploring a master's thesis behind the design of a DC to DC step-up converter for a racing motorcycle. It's honestly a perfect case study in how complex power management solves very real, very fast physical problems.
Here's a quick roadmap for our explainer today. First, we'll look at the electric racing challenge. Then, we'll break down exactly what a boost converter is. After that, we'll get into designing for motor student rules, and finally, we'll explore different converter categories.
All right, kicking things off with Section 1, the Electric Racing Challenge, or battery drain versus speed.
So, here's the million-dollar question. How do you maintain top speed when your battery is naturally dying over the course of a race? Think about it. In a traditional combustion engine, burning fuel makes the bike lighter, which can actually make you faster. But in electric racing, a draining battery introduces a really critical handicap.
And the core problem here is voltage sag. As a battery discharges, its voltage inherently decreases. That's just physics. And because the motor relies on that voltage, a drop in voltage means a direct reduction in available motor power. Basically, it kills your top speed. You can't just slap a fixed gear ratio on the bike or rely on a basic battery management system to fix this mid-race. If your voltage sags, you lose. It's really that simple.
So, the ETSNEB racing team, who are building a prototype for the Moto Student competition, they needed a custom fix. Their thesis proposes integrating a high-efficiency DC to DC step-up converter right into the motorcycle's powertrain. The goal is dynamic. As that battery voltage inevitably sags, the converter steps in, boosting it back up to maintain a constant output voltage to the motor. And the benefits? They're massive. You get sustained top speed, keeping the bike highly competitive. The rider gets much greater strategic control over their power deployment. Plus, a highly optimized converter minimizes energy losses in the powertrain, which is absolutely vital when literally every joule of energy counts.
Moving right along to Section 2. What exactly is it? The boost converter.
What's really wild is just how simple the core technology actually is. This is a pulse-width modulated, or PWM, boost converter. It transforms a lower DC input into a higher DC output using just a few basic components. We're talking an inductor, a transistor acting as a switch, a diode, and a capacitor. I know, it doesn't look like much, but this specific configuration is an absolute powerhouse for energy management.
So how does it work? Well, it builds into an actual boosting process that happens in three really elegant mechanical phases. First up is the charging phase. The transistor switch turns on, the diode blocks the path to the load, and the inductor draws power, storing that energy as a magnetic field. Then comes the boosting phase. The transistor turns off. Now the inductor naturally resists the sudden change in current, so the stored energy is forced through the diode, and the inductor's voltage is actually added to the input voltage. Boom, we have a boost. Finally, maintaining output. The capacitor steps in, acting like a reservoir to smooth out those pulsating boosts into a nice, stable, elevated DC voltage for the motor.
And it's worth pointing out that this continuous conduction mode technology isn't just for racing motorcycles. It is a massive backbone of modern industrial applications. We see it in clean energy, elevating lower voltages from solar panels so they can feed into the grid. We see it in UPS systems, providing backup power during outages. It's literally in your car right now, boosting battery voltage to power those high-intensity discharge headlamps. It is even a critical component in powering our entire global telecommunications infrastructure.
All right, Section 3, Moto Student Rules and Designing for Safety.
Now, the ETSIB racing team isn't just building this in a lab for some theoretical grade. They are designing a legit prototype for the Moto Student International competition. This is a real-world, high-stakes environment. University students from all over the globe build racing motorcycles that are aggressively tested on the professional Motorland Aragon circuit over in Spain.
And when you're racing at those kinds of speeds, safety is absolutely paramount. Which brings us to a very, very important number, 126. That 126 represents the absolute maximum voltage direct current allowed in the prototype by Moto Student regulations. To put that in perspective, anything over 60 volts is classified as high voltage. So crossing that 126-volt threshold, that means instant disqualification, or, worse, a severe safety hazard.
The rules also demand really intense safety isolation. The high-voltage system has to be completely electrically separated from the prototype chassis and any external metallic parts. So the ETSCIB engineers had a serious challenge, balancing the need for maximum boosted power against this absolute, hard regulatory ceiling.
Which leads us nicely into Section 4, Converter Categories and Architectural Choices. The thesis actually includes a really deep literature review of the architectural choices available to engineers.
First up, engineers have to choose between isolated and non-isolated converters. Isolated converters use transformers to create a very high degree of electrical separation. This makes them incredibly safe and low noise. They are perfect for super-sensitive applications like aviation, military, or medical devices. Non-isolated converters, on the other hand, might share a ground or use a floating output. They definitely have lower electrical separation, but they are so much more compact and cost-effective. That makes them hugely popular for non-isolated DC applications where space and weight, like, say, on a racing bike, are at an absolute premium.
Take a 3-level boost converter, for example. It is a fantastic example of a non-isolated topology that utilizes a floating output rather than a shared ground. It really showcases how engineers can get creative using just a few capacitors and switches to manage voltage dynamically, completely avoiding the heavy bulk of a massive isolation transformer.
Next, the design has to consider the actual direction of power flow. Unidirectional converters are awesome because they feature a much simpler design and generally have higher efficiency. If you only need to push power one way, from the battery to the motor, they are perfect. But if you need regenerative braking, which pushes power back into the battery, you're going to need a bidirectional converter. These utilize 2-quadrant switches to let power flow both ways. They give you incredible flexibility for charging and discharging, but that definitely comes with a trade-off. You're looking at a higher complexity and slightly lower efficiency because of switching losses.
And finally, let's look at the power source architecture. Voltage-fed converters are built with the capacitive input filter. Traditionally, they are designed to step down a higher input voltage to a lower output. But for our racing motorcycle, we absolutely need a current-fed converter. These are built with an input inductor, just like that simple PWM circuit we looked at earlier. That input inductor is exactly what makes them so incredibly effective at stepping up or boosting those lower input voltages to give the motor the sheer power it craves.
Ultimately, as the thesis really drives home, efficient power conversion is crucial in electric vehicles to enhance overall performance and reduce energy losses. Winning a race isn't just about throwing the biggest, heaviest battery you can find onto a chassis. It is about how smartly, how efficiently, and how dynamically you manage the power you actually have. By utilizing a highly optimized boost converter, the ITSCIB team ensures that every single drop of electrical potential translates into sustained speed on the track.
So I want to leave you with this thought. We've seen how this incredible technology is keeping racing motorcycles at their absolute peak performance. But knowing that these exact same principles apply to solar grids and telecommunications, how else might this hidden boosting technology secretly be optimizing the gadgets you rely on every single day? It's a powerful reminder that sometimes the biggest boosts in performance come from the smallest, most intelligently designed components. Thanks so much for joining me on this explainer, and keep exploring.